Hey there, I'm CL Fisher, and if you're here, you almost certainly already know about my show, Random Encounters, running from January 1st to 31st, 2021, at the At Origin Coffee Shop, 687 Mount Pleasant Road, Toronto, Ontario. If you're in the neighborhood, check it out. They're still doing takeout coffee during lockdown, and you can look at the physical pieces while you wait. I'm not much of a coffee person myself, but my friend who is says it's delightful. So, this is a deep dive into how the piece Twister was made. You may find that some parts are not deep enough and others are way too much information. If you have strong feelings on a subject, please let me know. There are comments around here someplace. Please feel free to fast forward if I'm going deeper than you want. For the really very techie among you, I'm currently using C++. Bits of this were originally developed in Ruby and Python, but I switched over to C++ for speed because some parts of this scale really, really poorly. Please note, I'm going to assume you're familiar with Oz, specifically with the 1939 MGM musical. It's okay if you haven't seen it. I'm not going to go into great detail on the decisions that are obvious if you have seen the movie, though. Twister incorporates things I've been coding for the last 3 years. There really isn't much new in it, I've just combined things. In order, I'll talk about pixel sorting for the background, how I make individual shapes in the Twister, how I choose the color for each blob, how I make them fit together in a swoopy way, and how I confine that swoop more or less to a cyclone shape while still having it be randomly determined. The background is based on a scene from the 1939 MGM musical The Wizard of Oz, showing a cyclone approaching the farm. I had to resize it to match the size of the end piece. So I had the code on hand to do the background work from my Dimensions and Canute pieces, which both have a horizon in them. They both work on the idea that every pixel in the piece belongs to a different sort region. You can definitely do this differently by just thinking about whether a pixel is above or below the horizon. So, first, I assign a region number to every pixel in the image according to whether they are above or below the horizon. Then I determine an offset. This offset determines what pixels get compared to each other in the next step. The offset is randomly determined based on some parameters that I feed in. The code for that is just the result of me mucking about until I got something I liked a couple of years ago. It has no real rhyme or reason, but it gives the effect I want, and I'm a little leery of changing it at this point. So then I walk through the image pixel by pixel. For each pixel, I get the next pixel at the offset. Then I ask, should I swap these? I swap them if they are in the same region and the color of the first pixel is greater than the second. In a monotone image like this essentially means darker than. So if you have a very light pixel in the top left, it'll get evaluated again later because it's been switched, and it can end up traveling several steps towards the bottom right. The offsets govern the direction of that movement to some degree. Then I get a new offset. The offset, as I said, is randomly determined, but it is constrained. If it were totally random, I'd never get to the end of the process, and the results would pretty much just be a blur. So I walk through the image again, and again, and again. I keep doing this until either time runs out, as I have a time limit of 4 hours in my parameters, or I have done as many repetitions as I decided to. I didn't put a limit on this one, or there are only a set percentage of the pixels moved on the current pass, in this case 1%. Now I did this quite small, just 800 by 1000 pixels, and blew it up to the 16 by 20 required for the project. There's a blurring aspect later on, so that pretty much eliminates the finer points that I would have had with the extra many hours of process. Okay, so that's the background. The next part is how the little blobs that represent the words are shaped. The blobs are based on L. Frank Baum's The Wonderful Wizard of Oz. So, this is the bit where I'm going to go into the most detail. There is trigonometry, but it's all based on 60-degree angles in this particular example, so it's not too bad. If you're math adverse, just insert CL's special sauce wherever you hear sine or cos, and you'll be fine. I'm going to take one word and run through how it is made into a shape. I picked the word I was going to show you based on the number of letters to make the trig easy, and that it has a capital, just because that makes it more interesting. The word is anti, for anti-M. Note, I'm going to try to use the American pronunciation because it's an American fairy tale, but my usual pronunciation of that word is auntie. So, anti. How do we make the shape for anti? Now, the sides of the shape are determined by the difference between each letter and a reference letter. I used capital J. Now, why capital J? I've tried lowercase a and capital A, and something in between seems to work best. What do I mean by difference? Well, each letter is represented in the computer by a number. For instance, this is called the ASCII code. For instance, lowercase a is 97 and uppercase A is 65. So I mean the difference between the number for that letter and the value for capital J, which is 74. Sometimes this will be a negative number. The angle between the sides is determined by the number of letters in the word. We start off pretending that it's a regular polygon with, since there are 6 letters, 6 sides. We know it's not going to be one, but we kind of pretend that it's going to be. So that would mean the angle that we need to work with is 60. There are actually going to be 7 sides, as you'll see. So we start with the letter A. Its ASCII value, the value the computer knows, is 65. The difference from J is -9. So we're actually going to be going in the opposite direction than we think to start off. The angle is 60, which means that we're going to have a line that goes from our start position minus 4.5 units across and minus 7.8 units down. I started with the hardest example first, I'm afraid. Here's the trig part. You need to multiply the length of the difference from the letter from J, that's -9, times the cosine of 60, that's 1/2, to get the horizontal displacement. And times the sine of 60, that's about 0.866 to get the vertical displacement. So, another thing. You might be used to thinking of up as positive, but when you're working with computer graphics, down is positive. Just another thing to have to remember. Sorry about that. But, I mean, the computer takes care of it. Okay. First, so we have the first side. Next, we do the same thing for lowercase u. I'm just going to fill in the chart. Note that the difference is now a positive number, and the angle is now 120. That gives us this side, and so on. This is one of the reasons I chose a 6-letter word. Some of the lines get to be horizontal, so it's easier to draw. And so on, and so on, and so on. But now we've run out of letters. It's okay. We just finish up by attaching the last point back to the start. And yes, this is an odd looking shape. Luckily for me, the graphics library I use, Magic++, is smart enough to fill that in the obvious way. Most words are going to give shapes that are more conventional shapes. Anything that's all lowercases is just, it's going to be more normal. But you are almost always going to have one more side than the number of letters. Unless you have just one letter, in which case I have to put a little kludge in to make it a three-sided figure.